A worker is pushing a 50 kilogram crate at a constant velocity over level ground by applying a horizontal 300 Newton force to it. So in part A, you're going to start by drawing the free body diagram for the crate. So we have a gravitational force going straight down, a normal force going straight up, and it turns out those two forces are equal to each other. Then we have an applied force in the direction that the worker is pushing the crate, and a frictional force opposing the motion. And we know that those two forces are equal to each other, and we also know that the frictional force is less than the normal force, so we are drawing the horizontal arrows a little bit shorter than the two vertical arrows. In part B, are the forces on the crate balanced or unbalanced? Since it tells you in the problem that the crate is moving at a constant velocity, that means the forces are going to be balanced. Remember, the two ways that the forces can be balanced are if an object is not moving or if it's moving at a constant velocity. The only way the forces will be unbalanced is if the object is accelerating. So because this is moving at a constant velocity, we can say that the forces are balanced, and you can put that for your justification of the answer. It tells you in the problem the crate is moving at a constant velocity. Part C, is the frictional force acting on the crate greater than, less than, or equal to 300 newtons? Well, we already know that the applied force right here is equal to 300 newtons, because that was given in the problem, and we know that the frictional force is equal to the applied force, since the forces are balanced, which means that the frictional force has to equal 300 newtons. And you can put for your justification that the forces are balanced, therefore FA is equal to FF. The applied force is equal to the frictional force. Part D, can the coefficient of static friction be calculated using the information given? Since the crate is in motion at a constant velocity, we're dealing with kinetic friction, so we cannot tell anything about static friction. So no is the answer, and the justification is the crate is moving, so we're dealing with kinetic friction only. So we can only look at stuff associated with kinetic friction. Then part E, can the coefficient of kinetic friction be calculated using the information given? And since there is only one value associated with kinetic friction, and the crate is moving, the answer is yes, we can calculate it. And the way to do that is, let's set up the problem, which is, well, let's set up the equation for friction, which is the force of friction is equal to mu k, the coefficient of kinetic friction, times Fn. So let's rearrange this equation to get the mu k by itself. So mu k is equal to the force of friction divided by the normal force. And we said earlier that the frictional force is 300 newtons. That was in part C. And we know that the normal force is equal to the gravitational force, since the two vertical forces are balanced. And the gravitational force is just m times g. So it tells you in the problem that the crate is 50 kilograms, and g on Earth, we're just going to use 10. So the gravitational force, and thus the normal force, is 500 newtons. So I'll put that down here. So the coefficient of kinetic friction is 300 newtons divided by 500 newtons, which is equal to 0.6. And remember, the coefficients of friction do not have units. So now the crate suddenly reaches a slick spot where the friction is negligible, but the worker continues to apply the same 300 Newton force to the crate. So in part F, we're going to draw a new free body diagram. So it's going to look a lot like the previous one, which is a gravitational force going down, a normal force going up, and those two forces are equal. The worker is still applying the same horizontal applied force, but now the frictional force is gone because it's on the slick spot, so we're not going to have a force over on this left side of the free body diagram. So part G, are the forces on the crate balanced or unbalanced in this new situation? And now there's no force opposing this applied force, so that means that the forces are unbalanced. And you can just put for your justification, the applied force no longer has a frictional force or any other force to balance it out.